Click the bell icon to get latest videos from Ekeeda.
Hello friends, so today we are here to learn about the eigenvalues and eigenvectors. So in this particular topic, we are going to learn about what is eigenvalue and what is eigenvectors and how they are related and what are the characteristics and the theorems related to it. So before understanding what is eigenvalue and eigenvector, let us consider square matrix. So eigenvalue and eigenvector is found out for each and every square matrix. It could be 1 by 1, it could be 2 by 2, it could be 3 by 3 as well. So if a matrix is not a square matrix, then the eigenvalue and eigenvector cannot be found. So eigenvalue and eigenvalues and eigenvectors, these are the special properties of a square matrix. So in order to understand, let us get aware, let us get familiar with few terms. Suppose if we have got A as square matrix of any order n cross n. That means there are n rows and n columns, where I is any unit matrix of same order n cross n. Let lambda be any value or the characteristic value which is called eigenvalue, and x as denoted as eigenvector for that particular eigenvalue. Now if we have got 3 by 3 matrix, then we have got 3 eigenvalues and 3 eigenvectors. So if we have got n by n square matrix, then we have got n eigenvalues, and each and every eigenvalue gives birth to each and every eigenvector, corresponding eigenvector. So we have got n eigenvectors. But before that, let's get aware of what is eigenvalue. So we need to consider any equation which satisfies mod of A minus lambda I, where A is the n by n square matrix, I is nothing but the unit matrix of the same order. Then we are supposed to calculate A minus lambda I, and if we take mod or determinant of A minus lambda I, then it is called characteristic equation. Or characteristic polynomial. When we equate this particular mod of A minus lambda I is equal to 0, then we get characteristic equation, and the roots of this equation are called eigenvalues or latent values or characteristic values. So in throughout these chapters, we are gonna call these roots are eigenvalues, and for each and every particular eigenvalues we have got eigenvectors. So let us understand what is eigenvalue and eigenvectors and how they are calculated. We'll take an example, and with the help of that example we'll solve this. Let us start with 2 by 2 matrix. Let us A is equal to 1, 2, 3 and 4. So this is 2 by 2 matrix, and I am supposed to find out what is the eigenvalue for the same. So as I said, if there is n by n matrix, then there are corresponding n eigenvalues are possible. So here we have got 2 by 2 matrix, so there are 2 eigenvalues are possible, and for each and every corresponding value there are 2 eigenvectors. So let us solve this. So A is 1, 2, 3, 4, and we are supposed to consider the characteristic equation as A minus lambda I is equal to 0. Therefore, let us calculate what is A minus lambda I first. So A is equal to 1, 2, 3, 4 minus lambda into I is nothing but the unit matrix of the same order. The order is 2 by 2. So unit matrix would be 1, 0, 0, 1. So that is nothing but 1, 2, 4, 3 minus, when lambda gets multiplied to each and every value of the matrix. So lambda into 1 is lambda, lambda into 0 is 0, 0 and lambda. So we have got 1, 2, 4, 3 and lambda 0, 0 lambda. So I'll subtract corresponding elements. So I'll be getting 1 minus lambda. 2 minus 0 is 2. 4 minus 0 is 4. And 3 minus lambda is 3 minus lambda. So in short, we can subtract this particular lambda value, that is eigenvalue, from all the diagonal elements, and we can directly arrive to this step. So 1 minus lambda, 3 minus lambda and 2 elements are as it is. Okay, so now let us consider this equation. Since A minus lambda I, determinant of A minus lambda I is equal to 0, therefore determinant 1 minus lambda, 2, 4 and 3 minus lambda is going to be 0. Therefore, as we know how to calculate the determinant or the value of the determinant as cross multiplication minus this. So 1 minus lambda into 3 minus lambda minus 2 into 4 is equal to 0. Therefore, so 1 gets multiplied with this and minus lambda now gets multiplied with this particular bracket. So 3 minus lambda and minus 2 into 4 is 8 is equal to 0. Therefore, this is 1 into 3 minus lambda is 3 minus lambda minus 3 lambda and minus lambda is plus lambda square minus 8 is equal to 0. Therefore, we'll be having lambda square minus lambda minus 3 lambda is minus 4 lambda, and this is 3 minus 8 is equal to minus 5 is equal to 0. So now using the calculator, we go to equation part and we solve the equation ax square plus bx plus c, as we put the value a as 1, b as minus 4 and c is equal to minus 5. Therefore, we get the values as lambda minus 5 into lambda minus 1 is equal to 0. So we'll factorize this. So product should be minus 5 and addition should be minus 4. So all possible combinations are minus 5 and 1. So lambda minus 5 and lambda plus 1. So therefore, when a into b is equal to 0, either a has to be 0 or b has to be 0 or both have to be 0. Therefore, lambda minus 5 is equal to 0 or lambda plus 1 is equal to 0. Therefore, lambda is equal to 5 and lambda is equal to minus 1. So these are the eigenvalues we have obtained for 2 by 2 matrix. Now let us move further and calculate what are the eigenvectors for this particular value. So each and every eigenvalue gives birth to each and every corresponding eigenvector. So let us consider first case 1 as lambda is equal to 5. Lambda is equal to 5. Now we know what is the characteristic equation is a minus lambda I into x is equal to 0, where x is an eigenvector. So therefore, we know what is a minus lambda into I, which is nothing but. Now what is the value of lambda over here? So let us calculate now. 1, 2, 3, 4 and here we have taken lambda as 5. So 5 into 1, 0, 0, 1 is equal to 0. Therefore, 1 2 3 4 minus 5005 is equal to 0. So let us understand this by using the actual case, which is case number 1 for lambda is equal to 5, which is the first eigenvalue. So case 1, lambda is equal to 5, and the eigenvector is found out by using a minus lambda I into x is equal to O. This is not 0, this is O. So for lambda is equal to 5, now a minus lambda I would be, what is the value of 1 minus 5, 2, 4, and this is 3 minus 5 into x, which is x1, x2 is equal to O, which is 0 and 0. Therefore, the values are 1 minus 4 is 5 is minus 4, and here we have got 2, here we have 4, and 3 minus 2 is minus 2 into x1 comma x2, and we have got 0 comma 0. So if we solve this particular equation, therefore minus 4x1 plus 2x2 is equal to 0, and 4x1 minus 2x2 is equal to 0. If you observe this carefully, minus 4x1 plus 2x2 is equal to 0, and if we multiply this particular equation by minus 1, I'll get this. This is plus 4, this is minus 2, and this is going to be 0. So we'll consider any of the equation, that is 4x1 minus 2x2 is equal to 0. Therefore 4x1 is equal to 2x2. Therefore 2x1 is equal to x2. So let us consider, let us take x2 is equal to t, and therefore 2x1 is equal to t. Therefore x1 is equal to t by 2, and therefore eigenvector x is nothing but x1 and x2, which is nothing but t by 2 comma t. Now I can have t common, so which is 1 by 2 and 1. Now I can multiply this by 2, and I can have t as half into 1. We can put now t is equal to 2, and we'll be having therefore x1, as this is the first vector, x1 as 2 into 1 by 2, which is going to be 1, and 2 into 1, which is going to be 2. So x1 as 1 comma 1 and 2 is going to be an eigenvector for this particular value lambda is equal to 5. Now let us calculate another eigenvector for the second value, which is lambda is equal to minus 1. Now for the case 2, lambda is equal to minus 1, we have got a minus lambda into I into x is equal to 0. Therefore I have got 1 minus minus 1, second element as it is, third element as it is, and fourth element as 3 minus minus 1 into x1 x2 is equal to 0 comma 0. Therefore we have got 1 plus 1 is equal to 2, again 2, because minus minus becomes plus, so 1 plus 1 is 2, 2 as it is, 4 as it is, and then 3 minus minus plus, 3 plus 1 is 4. So we have got x1 and x2 as 0 comma 0. So if we multiply this into this is equal to 0, we'll get therefore 2x1 plus 2x2 is equal to 0, and 4x1 plus 4x2 is equal to 0. If I take 2 constant and divide by this, I'll get x1 plus x2 is equal to 0. So as you can see, we have got 2x1 plus 2x2 is equal to 0 and 4x1 plus 4x2 is equal to 0. So if I take 2 common and divide by this, so I'll be getting x1 plus x2 is equal to 0, and if I take 4 common and divide by this, we'll be getting x1 plus x2 is equal to 0. So these two equations are same, which is nothing but x1 plus x2 is equal to 0. Now if I take x2 on the right hand side, I'll be getting x1 is equal to minus x2. Now we put x2 is equal to t, so we'll be getting x1 is equal to minus t. So as x2 is the second eigenvector for this particular second eigenvalue, so we have got x2 as x1 and x2. x1 is equal to minus t, x2 is equal to t, so we can take t common. I'll be having minus 1 and 1. Now we put t is equal to 1 and I'll be getting minus 1 and 1. This is the second eigenvector. So for the value lambda is equal to 5, we have got x1 as 1, 2. First eigenvector is 1, 2, and for case 2, lambda is equal to minus 1. For this particular eigenvalue, we have got x2 as minus 1 and 1, which is the second eigenvector. So we solved 2 by 2 matrix for 2 eigenvalues and 2 eigenvectors. Now let us focus on square matrix, which is of order 3 by 3. So let us consider this example. Find the eigenvalues and eigenvectors of the following matrix A. So solution starts. As we all know, A minus lambda I is nothing but the characteristic equation. Therefore, from all the diagonal elements, we are supposed to subtract lambda, and this is the shortest way of solving it. 8 minus lambda, other values remain as it is. This is 4, this is minus 3 minus lambda and minus 2. 3 minus 4 and 1 minus lambda is equal to 0. Now to solve this determinant, we can have first element taken, which is 8 minus lambda into, will leave this row and this column and this particular things we have in our hand. So minus 3 minus lambda into 1 minus lambda minus 2 minus 4 minus second element, which is minus 8 into, will solve this by eliminating this first row and second column. So we have got 4 minus 2, 3 and 1 minus lambda. So 4 minus 1 minus lambda minus 3 into minus 2. So we have got minus 8 into 4, 4 minus 1 into lambda minus 3 into minus 2, and minus 2. This is plus minus 2 into, will leave first row and third column, and we are left with 4 into minus 4 minus 3 into minus 3 minus lambda is equal to 0. Guys, you can see this equation becomes tedious or cumbersome, so we cannot solve this equation by easiest method. So each and every time I'll have to multiply this, sort it out, and then multiply by each and everything. So there are many multiplications are involved, and there are higher chances of getting mistaken with each and every step. So basically what we'll do, there is a formula for the same. Therefore lambda cube minus sum of diagonal elements into lambda square plus lambda into minors of diagonal elements minus mod of A is equal to 0. So this is the simplest equation, and we are going to use the same. We are not going to perform this particular calculation anymore. So let us understand what it is. Lambda cube minus sum of diagonal element, that is 8 plus minus 3 plus 1, which is going to be 6. Now this sum of the diagonal elements. Now sum of the diagonal elements is also called a trace of a matrix. Trace, T-R-A-C-E, trace of a matrix. So this is the sum of the diagonal elements, minor of diagonal elements, and the addition of the minors. So let us start with this. Lambda cube minus sum of diagonal elements, which is going to be 8 plus 1 minus 3 into lambda square plus lambda into minors of diagonal elements. So let us consider 8, and the minor of this would be, leave this row and this column. I am left with 3 minus 2 minus 4 and 1. The determinant value of this particular elements or this determinant gives me the minor for 8. Plus we'll consider minus 3 and calculate the minor for this, and plus we'll consider 1 and minus for this, minor for this, and we'll add all the minors. So let us consider 8. We'll leave this row and this column. Now I am left with minus 3, minus 2, minus 4 and 1. So minus 3 into 1 is minus 3 minus the multiplication of this, which is 8. So minus 3 minus 8 is minus 11, plus we'll consider minus 3. Minus 3 comes in row 2 and column 2. Now we'll leave those row 2 and column 2, and I am left with 8 minus 2, 3 and 1. So 8 into 1 is 8 minus minus 6. So 8 plus 6 is plus 14, plus we'll consider third element. We'll leave this row and this column. 8 minus 3 is minus 24 minus minus 32, which is 32 minus 24, which is plus 8 into lambda. Now we have got plus mod of A, which you can directly put in the calculators. The values 8 minus 8, 2, 4 minus 3 minus 2, 3 minus 4 and 1. Here you will get the value 8 minus 8 minus 2, 4 minus 3 minus 2, 3 minus 4 and 1. By putting these values into calculator, you will get the determinant value as 6. And here it should be plus, minus, plus, and here it should be minus, so minus 6. Therefore, you will get lambda cube 8 minus 3, 5 plus 1 is 6 minus 6 lambda square minus 11 plus 14 is nothing but 3 plus 11, and this minus 6 is equal to 0. Now again I'll put this equation into calculator using ax cube plus bx square plus cx plus d is equal to 0 with the coefficients 1, minus 6, 11 and minus 6. Therefore lambda is equal to, I'll get 1, 2 and 3. So these are the eigenvalues for this particular eigenvector. Lambda is equal to 1, 2 and 3. These are the eigenvalues of this particular matrix A. So let us take case 1, which is lambda is equal to 1, and solve the eigenvector lambda is equal to 2 and lambda is equal to 3. Lambda is equal to 1. Therefore, A minus lambda I into x is equal to O. Therefore, we'll subtract lambda is equal to 1 from all the diagonal elements. So which is, I'll get 8 minus 1, 7, minus 8, minus 2. 4. Minus 3 minus 1 is minus 4, minus 2. 3, minus 4 and 1 minus 1 is 0. As x1, x2 and x3 as 0, 0, 0. Now in order to solve this, we can consider any two equations and solve this by using Cramer's rule. So let us write down all the equations first. Therefore, this row into this column is equal to 0. Therefore 7x1 minus 8x2 minus 2x3 is equal to 0. 4x1 minus 4x2 minus 2x3 is equal to 0. And here 3x1 minus 4x2 plus 0x3 is equal to 0. Now we can consider first two equations, and by using Cramer's rule we'll solve this. What Cramer's rule says, you consider unknowns x1, x2, x3. You equate it with alternate plus minus sign, plus 1 minus 1 plus, so equal to and equal to, and this is nothing but divided by determinant, divided by determinant, and divided by determinant. Now x1, if you observe first two equations, for x1 you leave this part, you hide x1 and x1, you are left with minus 8, minus 2, minus 4, minus 2. Minus 8, minus 2, minus 4, minus 2. And for x2, you hide this part, you are left with 7, minus 2, 4, minus 2. And for x3, you hide this part, you will be having 7, minus 8, 4 and minus 4 is equal to, let's say, k. Therefore, we'll solve this. X1 divided by, what is the value of this determinant? Minus 8 into minus 2, which is 16, and 16 minus 8, which is going to be 8, is equal to minus x2 divided by 7 into minus 2, which is minus 14, minus 8, which is plus 8. So minus 14 plus 8 is going to be minus 6, is equal to x3 divided by 7 into minus 4, which is minus 28, minus 28 minus minus 32, which is plus 32. 32 minus 28 is going to be 4. Therefore, I am having x1 is equal to 8 into k. x2 is going to be 6 into k, because minus minus sign is gone, and x3 is equal to 4k. Therefore, x1, which is the first one, first eigenvector, it becomes 8k, 6k and 4k. Now we can take 2k common. Now we can take 2k common from this, and we'll be getting, therefore x1 is equal to 2k into 4, 3 and 2. Now we'll put this k is equal to half. We get x1 is equal to 4, 3, 2. So this particular x1 is equal to 4, 3, 2 is the first eigenvector of the particular value lambda 1 is equal to 1. Now let us focus on lambda is equal to 2, which is the case number 2. Now again we'll start with a minus lambda I into x is equal to O. Therefore, so for case 2, lambda is equal to 2. We'll consider a minus lambda I into x is equal to 0. For lambda is equal to 2, we'll subtract lambda from each and every diagonal element and we'll write the equation. So 8 minus 2 is 6. Other elements are as it is, minus 8, minus 2, 4, minus 3, minus 2, which is minus 5, and minus 2. Last is 3, minus 4, and 1, minus 2, which is nothing but minus 1. So, this into x1, x2, and x3 is equal to 0, 0, 0. As you can see, 3, minus 4 and minus 1. If you multiply this with 2, you will be getting 6, minus 8 and 2. So these two equations are nothing but same, that is row 1 and row 3. But row 2 equation is different. So we can consider first two equation and use Cramer's rule on it. So therefore Cramer's rule, we have got 6x1 minus 8x2 minus 2x3 is equal to 0, and 4x1 minus 5x2 minus 2x3 is equal to 0. So by Cramer's rule, what do I have? X1 divided by particular determinant is equal to minus x2 divided by particular determinant is equal to x3 divided by particular determinant. Now for x1, we hide x1 and we'll be writing minus 8 minus 2 minus 5 minus 2. For x2, we'll write 6, we'll hide this x2 and we'll write 6 minus 2 and 4 and minus 2. For this x3, we'll hide this and we are having 6 minus 8, 4 and minus 5. Now, we'll calculate the values for the same. So, x1 divided by minus 8 into minus 2, which is 16, 16 minus 10, which is going to be 6. Therefore, x1 divided by 6 is nothing but minus x2 divided by 6 into 2 is minus 12, minus 12 minus 8, which is minus minus, plus 8, which is going to be minus 12 plus 8, which is going to be minus 4, is equal to x3 divided by 6 into 5 is minus 30, minus 30 minus minus 32, which is plus 32, and 32 minus 32 is 2, is equal to k. So I'm having the equations now. Therefore, x1 divided by 6 is equal to x2 divided by 4 is equal to x3 divided by 2 is equal to k. Therefore, x1 is equal to 6k, x2 is equal to 4k, and x3 is equal to 2k. Therefore, this x2, this particular second eigenvector, can be written as 6k, 4k and 2k. Now I can take 2k common. Therefore, x2 is equal to 2k common, and I am left with 3, 2, 1. Now we'll be put k is equal to half. We get x2 is equal to 3, 2, 1. This is the second eigenvector for this second particular value. Now we'll focus on case 3, which is lambda is equal to 3. Case 3 is lambda is equal to 3, and characteristic equation is a minus lambda I into x is equal to 0. Now we'll subtract lambda is equal to 3 from the original matrix. Now let us look at original matrix. It is 8 minus 8 minus 2, 4 minus 3 minus 2, and 3 minus 4 minus 1. So I am going to subtract lambda is equal to 3 from the diagonal element, that is 8 minus 3 is equal to 5, minus 3 minus 3 is equal to minus 6, and 1 minus 3 is minus 2. So I am going to write the same. 3 minus 4 and minus 2. Now these three equations look distinct, that is they are not same as each other. So x1, x2, x3 is equal to 0, 0, 0. Therefore we can consider any two equations. Therefore let's consider first and second one. Therefore phi x1, this into this, phi x1 minus 8x2 minus 2x3 is equal to 0, and this into this, which is 4x1 minus 6x2 minus 2x3 is equal to 0. Now we'll use Cramer's rule. By Cramer's rule, we are going to have x1 is equal to divided by particular determinant is equal to minus x2 divided by particular determinant is equal to x3 divided by particular determinant. Now when we consider x1, we are going to hide these two terms and I am going to focus on -8, -2, -6, -2. Like that, when we hide x2, we are going to have 5, -2, 4, -2. And for x3, I am going to hide these two and I am going to focus on 5, -8, 4 and -6. Is equal to k. Therefore, let us calculate x1 divided by -8 into -2, which is 16, 16 minus 12, which is going to be 4, minus x2 divided by 5 into 2 is -10, -10 minus -8, which is going to be -2, divided by 5 into -6, which is -30, minus -32, which is +32, which is going to be 2, is equal to k. Therefore, x1 becomes 4k, x2 becomes 2k, as this minus minus sign is going to get cancelled, and x3 is equal to 2k. Therefore, x is equal to x1, x2 and x3, which is nothing but 4k, 2k and 2k. Now I am going to take 2k out. X is equal to 2k out, which is going to be 2, 1 and 1. Now I am putting k is equal to half. So x3 becomes 2, 1 and 1. So this is the third eigenvector for this particular value, lambda is equal to 3. So for lambda is equal to 1, therefore lambda 1 is equal to 1, lambda 2 is equal to 2 and lambda 3 is equal to 3. And the particular vectors x1 dash, x2 dash and x3 dash is going to be, for lambda is equal to 1, x1 dash is 4, 3 and 2, which is the first eigenvector. For lambda is equal to 2, x2 dash, which is the second eigenvector, which is 3, 2 and 1, and lambda is equal to 3, which is the third eigenvector, which is 2, 1, 1. And hence we have calculated 3 eigenvalues and 3 eigenvectors for square matrix of order 3 by 3. Let us come to 3 by 3 matrix again, where we have got eigenvalues which are repeated. In the previous sum which we saw, it was eigenvalues which were not repeated. So let us continue with the eigenvalues repeated and let us find out what are the eigenvalues and eigenvectors for the same. So we have got, find the eigenvalues and eigenvectors for A is equal to 2, 1, 1, 2, 3, 2 and 3, 3, 4. Now let us start with the characteristic equation, which is nothing but mod of A minus lambda I is equal to 0. Therefore, 2 minus lambda, we are going to subtract lambda from each and every diagonal element. 2 minus lambda, 1, 1, 2 and 3 minus lambda, 2 and 3, 3 and 4 minus lambda is going to be 0. Now, as I said, we won't be calculating this determinant by regular method, but will be applying special formula, which is as it is, lambda cube minus sum of diagonal elements into lambda square plus lambda into minors of diagonal elements minus mod of A is going to be 0. Therefore, lambda cube minus sum of diagonal elements, which is 2 plus 3 plus 4. 2 plus 3 plus 4 into lambda square plus lambda into minors of diagonal elements. Let us consider 2, and the minor is, leave this row and this column. You will be getting 3 into 4, which is 12. 12 minus 6 is 6. So 6 plus. Consider this 3. Leave this row and column. 2, 1, 3, 4, which is nothing but 2 into 4 minus 3 into 1, which is going to be 8 minus 3, which is 5. Plus, consider this 4. Leave this row, leave this column. 2 into 3, 6 minus 2, which is going to be 4. Minus the determinant of this particular matrix A, which is going to be 7, is equal to 0. Therefore, lambda cube minus 2 plus 3, 5 plus 4 is 9 lambda square plus 6 plus 5, 11 plus 4, which is 15 lambda minus 7 is equal to 0. If you solve this by using calculator, by putting ax cube plus bx square plus cx plus d is equal to 0, you are going to put the coefficients as 1, minus 9, 15 and minus 7 is equal to 0. Therefore, the values you will be getting is lambda is equal to 1, 1, 7. So here 1 is the value which has got repeated twice, along with 7 is the distinct value. So let us focus on lambda is equal to 1, which is the case 1. Now case 1 is lambda is equal to 1, and the characteristic equation is a minus lambda I into x is equal to O, which is the null vector or the 0 vector. Therefore, lambda is equal to 1. We are going to subtract lambda is equal to 1 from the original matrix. So let us have focus on original matrix. Original matrix was 2, 1, 1, 2, 3, 2 and 3, 3, 4. So I am going to subtract 2 minus 1 as 1, 3 minus 1 as 2 and 4 minus 1 as 3. So I will be getting 1, 1, 1, 2, 2, 2 and 3, 3, 3. 1, 1, 1, 2, 2, 2, 3, 3, 3 into x1, x2 and x3 equal to 0, 0 and 0. Now as you can see, 1, 1, 1, 2, 2, 2 and 3, 3, 3, these equations are nothing but same, because if you multiply this first row by 2, you will get second row. If you multiply this first row by 3, you will get third row. Therefore, there is only one equation possible, that is x1 plus x2 plus x3 is equal to 0. Now here we have got 3 unknowns and only one equation. Therefore, number of parameters we need to put is equal to unknowns minus equation is equal to 3 minus 1 is equal to 2. So there are two parameters s and t. So let us consider x2 as s and x3 as t. Now we have got equation x1 plus x2 plus x3 is equal to 0. Now let us put the values of x2 and x3, which is s and t respectively. So plus s plus t is equal to 0. Therefore, the value of x1 becomes minus s minus t. Therefore, x1 becomes x1, x2 and x3, where x1 is equal to eigenvector for this particular value, lambda is equal to 1. So minus s minus t, x2 is equal to s and x3 is equal to t. So which is nothing but, we'll consider minus s minus t. This is going to be s plus 0 and 0 plus t. So we'll be having 2 eigenvectors, minus s and 0, plus minus t, 0 and t. So I am going to take s common. So I'll be having minus 1, 0, and here I am going to have t common. So I am going to have minus 1, 0 and 1. Now let us put s is equal to 1 and t is equal to 1. So we'll be getting, therefore, x1 is equal to minus 1, 1, 0 and x2 is equal to minus 1, 0, 1. Here we have got two eigenvectors simultaneously, since the value lambda is equal to 1 has been repeated twice. So if it would have been repeated thrice, then we would have got all the three vectors in the same value. But since lambda is equal to 1 has been repeated twice, so we have got x1 and x2. Using this, we are going to put s is equal to 1. So I am going to get this particular vector separately as x1 and this particular vector separately as x2. Now let us come to case number 2. Lambda is equal to 7. And again the same characteristic equation, a minus lambda I into x is equal to O. Therefore, I am going to subtract lambda is equal to 7 from the original matrix. So let us examine original matrix. So original matrix is 2, 1, 1, 2, 3, 2 and 3, 3, 4. So I am going to subtract 7 from this. So 2 minus 7 is going to be minus 5, 3 minus 7 is minus 4 and 4 minus 7 is minus 3. So we'll be having minus 5, 1, 1, 2, minus 4, 2, 3, 3, minus 3 and x1, x2, x3 as 0, 0, 0. Now if we observe minus 5, 1, 1, 2 minus 4, 2 and 3, 3 minus 4, these are three distinct equations. There are no two equations which are alike. So we can consider any two equations for the using Cramer's rule. By Cramer's rule, we'll consider first two equations by convention, minus 5x1 plus x2 plus x3 is equal to 0 and 2 into x1 minus 4 into x2 plus 2 into x3 plus 2 into x3 is equal to 0. Therefore, let us consider x1 divided by determinant minus x2 divided by determinant is equal to x3 divided by determinant is equal to k. So x1 will leave this column and will be getting 1, 1, minus 4 and 2. If we hide this x2, x2 will be left with minus 5, 1 and 2 and 2. x3, if we hide this x3, minus 5, 1 and 2 and minus 4. Therefore, x1 divided by 1 minus 2 which is 2, 2 minus minus 4 which is equal to 6 is equal to minus x2 divided by 5 minus 2 is going to be minus 10 minus 10 minus 2 which is minus 12 is equal to x3 divided by 5 fours are 20 minus 2 is 18k is equal to k. Therefore, x1 is equal to 6k. Minus and minus sign will go. x2 is equal to 12k and x3 is equal to 18k. Therefore, x3 third eigenvector would be x1, x2 and x3, which is going to be 6k, 12k, 18k. Now I'll get 6k out. I'm left with 1, 2 and 3. Now we'll put k is equal to 1 by 6. Therefore x3 becomes 1, 2 and 3. So this is the third eigenvector for particular value lambda is equal to 7. Therefore for lambda is equal to 1, we have got x1 dash, this particular eigenvector, which is nothing but -1, 1 and 0. For second eigenvalue, which is nothing but 1, because it has got repeated twice, so I'm writing x2 dash, which is nothing but -1, 0, 1. And for lambda 3 is equal to 7, I'm having x3 dash, which is nothing but 1, 2, 3, which we have already calculated right now. So these are the 3 eigenvalues and 3 eigenvectors for 2 particular values which we have seen for repeated and non-repeated eigenvalues. Thanks for watching this video. Stay tuned with Ekeeda and do subscribe to Ekeeda.